Let's do that. Got it. Okay. Interesting. Are you not connected appropriately? Not much. There we go. Fixed it. Welcome, Caitlin. And yeah, chat as well. I'll say it again, I highly recommend bookmarking the website so you don't have to scan this thing every time. It's much easier that way. Oh, that cool. Every time. Funny how you can write yourself like a little page of notes and then just leave them in your office. I feel like I do it so frequently. I know what I'm talking about. Oh, I know what it was. Oh, that was interesting. Is there a handout There's not a handout today. Um, I'm not sure where I'm on. I will in the future, if I do make handouts, I will certainly post them on Canvas so that you can access them along with the class. Because I'll try to get them before class if there are handouts. Yeah. I will actually, so I will point out that a lot of the notes that I kind of refer to are from Grant's website. So like, for example, let me just actually pull this up here real quick. That's not where I'm going. Yeah, good. But the real truth is that I often use these notes for inspiration and then kind of change things up. So these aren't exactly what I'm usually doing typically. But for example, I would say that here real quick. So like I'm probably going to be referring to I would say that these three notes are the notes I'm going to be referencing on a lot of the class today. But really, you can find all this at Grant's website. I would encourage everyone to look at it. There's the attendance form. Again, I'll say to all of you, I would recommend bookmarking it so that you don't have to scan this thing every time, but it's perfectly fine. It's 9 o'clock. I guess we should get going. Yeah, all right. Pens, I need pens. So obviously we meet on Tuesday, Thursday, which means all of you are going to have your actual 17B class on Friday and Monday before I see you again. So there's going to be a lot of things you see between when I see you next. So that's why on Friday or Saturday, when you're doing the reflection for this class, you should be like, oh, I would really love it if we talked about blank on Tuesday. That's how I'm gonna, and now so to be honest, I'm also gonna look at um, I'm also going to look at what your professor has posted over the weekend. I definitely was watching Vidal's lecture from yesterday to kind of see what was going on. Also looking at Temur Galiava stuff as well. But if you tell me what you want to see, that's just going to be good for everybody. So definitely do the reflections. Let me know what you want to see, and we'll try to help you see the things you want to see. All right, let's talk a little bit more about antiderivatives, and then we'll jump right into the Riemann sum stuff and talk about how that all works. But I just want to clarify a couple things when it comes to antiderivatives. Let's do that. And let's move this down here a little bit so I can write on it in a way that makes sense. Yeah. Okay. I need to email my person about pens. So Co-17B. But before we get into it, real quickly, my brother's birthday today, April 4th. And just something interesting that you might not know about. You don't need to write this down at all, but I just want to tell everybody there's something called anchor days, which I think are really neat. And the following days, April 4th, June 6th, August 8th, my birthday, December 10th, October 10th, December 12th, all happen on the same day of the week each year. So this year, they're all on a Thursday. Next year, they're all on a Friday. And every year, they all happen to be on the same day of the week, which I just think is cool. Also, these days, 5/9 and 9/5, 7/11 and 11/7. Also Pi Day. Also the last day of February, which might be the 29th or the 28th, depending on if it's leap year or not. I just think it's neat, kind of cool. So if someone asks me like, what day is Christmas on this year? I'm like, well, December 12th is on Thursday. 2 weeks later, December 26th. So December 25th is going to be on a Wednesday. Kind of fun. That's all there is to say about Anchor Days, Phil. I think it's neat. There's my brother's birthday today. There's my birthday in August. Kind of cool. If you want to talk more about Anchor Days sometime, come see me. I'm happy to talk about calendar stuff anytime you like, because I think the calendar is really interesting. back to the Co-17B stuff. So let's briefly talk about antiderivatives and their notation. So if someone asks us to find, like, say, find the antiderivative, which is annoying to have to write in the first place, of f of x equal to cosine of 2x plus 5x, we get tired of writing this. So we're going to start defaulting to the notation that means the thing we want to, even though we don't really have all of the meaning behind it. So the way I would prefer to write this is to say find the antiderivative of cosine of 2x plus 5x. And then you slap on the dx at the end. And I would just say, for now, when you see this written, you should just think of those two things are just instructions. These are instructions telling us to anti-differentiate. It's a long word to write. That's all those things say. You could also use the capital notation, but really, we move away from that very quickly. So if I want to anti-differentiate this cosine of 2x plus 5x, well, here's what I'm thinking about. I know the antiderivative, and here's what I'm doing almost every time. When I have a more complicated inside piece of a function, in my head, I'm replacing that with x. I'm not thinking of cosine of 2x, I'm thinking of cosine of x. I'm saying to myself, I know the antiderivative of cosine of x is sine of x. So then the antiderivative of cosine of 2x is kind of like sine of 2x, but not quite. So let's specifically look at the antiderivative of cosine of 2x for just a second. My guess is that it's going to be sine of 2x. That's not right, because the derivative of sine of 2x, if I use the chain rule, I'm going to get cosine of 2x times what? Right. Oh, my derivative should have just been cosine of 2x if I wanted that to be the antiderivative. So to adjust for that, we're going to multiply both sides by the reciprocal of 2. 1/2. So the derivative of 1/2 sine of 2x is going to give me 1/2 times cosine of 2x times 2, which is just cosine of 2x. So since the derivative of 1/2 sine of 2x is equal to just cosine of 2x, then we can say that the antiderivative of cosine of 2x is 1/2 sine of 2x plus. I feel like I say this a lot, but what I really want to say is this pattern holds for all sorts of things. So if your inner part of your function is a multiple of x, we usually end up dividing by the coefficient of x. So for example, the antiderivative of e to the 4x. Okay, I'm not thinking of e to the 4x, I'm thinking of e to the x. And I know that the antiderivative of e to the x is kind of lovely, it's just itself. The antiderivative of e to the x is e to the x. So my wrong guess here is going to be that the antiderivative of e to the 4x is just e to the 4x. We'll deal with the plus c in a second. But we know that's not right, because we know that if we take the derivative of e to the 4x, that e to the 4x, not that one, the derivative of e to the 4x is e to the 4x times 4. But I wanted to just be e to the 4x. So I do the same thing I did before. I divide both sides by 4 or multiply both sides by 1/4. Either way you want to say it. Say, oh, I really need the derivative of 1/4 times e to the 4x to equal 1/4 times e to the 4x times 4. And then those cancel out. And since the derivative of this is equal to that, the antiderivative of that is equal to that. And then you can do this all sorts of times, right? Like we kind of just move along and say, well, I know these antiderivatives, like for example, we know that the antiderivative of secant squared of x dx is equal to tangent of x plus c. So then we could, in a similar way, figure out the antiderivative of secant squared of 6x. I want you all to write down your best guess. The right guess, not the wrong guess I've been doing, the actual right guess. Those of you in the chat, here's the attendance form again. Also, if you came in late and haven't filled out the attendance form, you can scan it there or there. Not the paper one, the laminated one. It'll look like the one for our class. They'll say like 16B or sorry, 16C or 17B or 21B. If you're somewhere else, it's not the right place. All right, so hopefully everybody is coming up with a guess of tangent of 6x. And you can either write it as tangent of 6x divided by 6, or if you prefer, 1/6 times tangent of 6x. Either way is fine. I probably default to putting the 1/6 out in front, but it doesn't really matter. Also, just a reminder, you're welcome to ask questions. If there's something you want me to clarify, say more about, I'm happy. Yeah. Was it like the x e to the x squared one? Yeah, okay, that's exactly where I was going next. Perfect lead-in. So let's look at something like this. What if I want now? So really what we're doing right now is we're kind of circumventing a process which is called U substitution, which we're going to learn about in a week or two. But the idea is that we know that the derivative, and I'm going to use the word stuff a lot. I use the word stuff as a replacement for a function. So instead of saying like the derivative of e to the f of x or e to the u, I often say e to the stuff. But you can write it a couple ways. You can say the derivative of e to the f of x is e to the stuff times the derivative of the stuff. If I'm saying the word stuff and I'm taking a derivative, I know at the end of the process, I have to multiply by the derivative of that stuff. That's why I say the word stuff, to remind myself I have to multiply by the derivative because of the chain rule. I'm saying the word stuff, the chain rule is in play. And U substitution is just undoing the chain rule, which we again will learn about next week or the week after. So the idea is that if you have something that looks like this, we know its antiderivative is exactly e to the f of x. So let's make an easy example to start off with, or easier, and then we don't have to adjust. So let's say I want to find the antiderivative of 3x squared times e to the x cubed. So it seems like a reasonable guess might be just the e to the stuff part. So let's ask ourselves, is it equal to e to the x cubed plus c? Well, let's check. The derivative of e to the stuff is e to that stuff times the derivative of that stuff. But the derivative of x cubed is exactly 3x squared. So we're good because the derivative of our antiderivative got us back to where we started. E to the x cubed times 3x squared. Yes, I wrote it in the opposite order of multiplication. Order of multiplication doesn't matter. I can write it as 3x squared times e to the x cubed or e to the x cubed times 3x squared. Either way is fine. Now, the problem he did in class was a little more complicated because we didn't have the perfect coefficient, right? The one in class was similar to like not having had the 3 here. This happens a lot. And so the nice thing about derivatives and antiderivatives is it's totally valid to multiply both sides of an equation by a constant and not affect anything else. You can multiply by a constant, divide, just like we've been doing this right here, right? This derivative, we multiply both sides by 1/4. Didn't change anything really other than we multiply both sides by 1/4. But it doesn't affect the fact of how you're differentiating or anti-differentiating. So let's look at another example of something like this. And yeah, we'll do that. That's good. Oh, we'll do that. Okay. So let's say we want to find the antiderivative of, sure, let's have some fun, x to the 4th times e to the x to the 5th. And here's how I'm going to think about it. I'm going to make my guess that I know is wrong. I know I've essentially got, and I'm going to say this a lot, the derivative of x to the 5th is essentially x to the 4th. Yeah, I know there's a 5 there, but I don't care about the 5 really. Like we care a little bit about the 5 and we're going to fix it at the end, but we're going to ignore it in the beginning. So right now I'm going to make my wrong guess that the answer is e to the x to the 5th. I know it's wrong. because we know, in fact, I want you all to write down on your own to find the derivative of e to the x to the 5th. Go ahead and do that. Not what I meant to press. Hopefully you're getting e to the stuff times the derivative of the stuff. And we're so close, right? This is, if I write it to look more like that, I've got 5 times x to the 4th times e to the x to the 5th. I'm off by a multiple of 5. So what do? Divide by 5 or multiply by 1/5. Same thing, really. So we can say that the derivative of 1/5 e to the x to the 5th is exactly 1/5 times 5 times x to the 4th times e to the x to the 5th. And then that's just x to the 4th times e to the x to the 5th. Sorry, derivative of 1/5 e to the x to the 5th is equal to x to the 4th e to the x to the 5th. So the antiderivative of x to the 4th e to the x to the 5th has to be 1/5 e to the x to the 5th plus c. That's what's happening. And there are other ways of doing it. So just to kind of show you a slightly different take on this, another way of seeing this would be to say, I'm going to rewrite that antiderivative as 1/5 times 5 times x to the 4th times e to the x to the 5th. Some people like doing it this way better. It's totally fine. And then we can see that, oh yeah, the derivative of e to the x to the 5th is equal to 5x to the 4th times e to the x to the 5th. So the antiderivative of 5x to the 4th e to the x to the 5th has to be e to the x to the 5th. Another way of getting to the same place. Plus c. Does that clear up what you was talking about in class a little bit? Yeah. And again, later on, we're going to talk about substitution, but even then, I would say, for examples like this, where you're just kind of off a constant multiple, it's almost easier to not use the longer process of U substitution and just say, I know I can just multiply or divide by what I need to fix it. Cool. All right, so moving away from anti-differentiation for a minute, or more than a minute, we're going to talk about kind of the reason behind. Eventually, we're going to circle back around to making the connection between taking antiderivatives and finding area under a curve, but we're going to talk about finding area under a curve. And yeah, sure. But before we do that, we need something else. Yeah, let's go there. So let's talk briefly about sigma notation. So finding sums, sigma notation. And I know I keep saying this, I really need to get some new pens. You can see the ink starting to run out here. I like these thicker pens because you guys can see what I'm writing better. Find the other one. I've got like 2 of them. Okay, so let's say we've got this. The sum from I equals 1 to 4 of I cubed plus 4I. So all this is, it's a compact way of writing something longer. So what this means is start at I equals 1. And this I cubed plus 4I is just a function of I. It's just instructions saying, okay, take your value of I and then cube it and then add 4 times it. So I'm going to get 1 cubed plus 4 times 1. And then you bump up to the next integer value. And I should really say to the next, no, it could be negative, I guess. The next integer value. Plus, then I equals 2. 2 cubed plus 4 times 2. Plus, then we go to 3. 3 cubed plus 4 times 3. And then we go to 4. 4 cubed plus 4 times 4. And then we go to stop, right? We stop because there's a 4 up there. So we start at 1, we end at 4. And what I want you to see, I don't really care what this adds up to. Like something. But watch how we can break this apart. I'm going to break this apart into 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. And then over here I have 4 times 1, 4 times 2, 4 times 3, 4 times 4, or 4 times 1 plus 2 plus 3 plus 4. Which I'm then going to actually go back to writing as separate summations. I'm going to write this first part here as the sum from I equals 1 to 4 of I cubed, plus 4 times the sum from I equals 1 to 4 of I. And so really, what I want you to see with this example is that when you have a sum of some things added together, you can break it apart into the constituent pieces added together, and you can also factor out any constant multiples. So importantly, summations, sigma notations, can be broken up, and constant coefficients can be factored out. We use this fact quite often. Well, quite often in this one little section where we're talking about using sigma notation. Cool. So then a couple things. There are some rules. I don't know if you actually have to memorize them or not, but we'll talk about them regardless. And I did see on at least the Dell's discussion sheet some proving of some of these rules, which I thought was not a bad question to ask. But let's look at this first one. Sum from, let's do that one first. I equals 1 to n of I. Starting, we're adding up, and we're just saying, okay, I'm going to get 1 plus 2 plus 3. And I just keep going forever and ever and ever until I get to, let's say, n minus 2 plus n minus 1 plus n. What does it add up to? Well, there's a really, really slick way of finding it, which I think is just super cool. So we're going to do it again. We're going to say the sum from I equals 1 to n is, but we're going to go backwards. We're going to start at 1 over here, plus 2, plus 3, plus dot, 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 all the way to n minus 2, n minus 1, n. Okay, and then we're going to add vertically. So this plus this is double that. So I have 2 of the sums from I equals 1 to n of I. Sorry, I forgot the I there. Okay, and here's the fun part. 1 plus n is n plus 1. Okay, not exciting yet, but 2 plus n minus 1 is n minus 1 plus 2, which is n plus 1. Okay, still not that exciting. But 3 plus n minus 2 is also n plus 1. And so it's 4 plus n minus 3 and 5 plus n minus 4 and so on and so on and so on, all the way to n minus 2 plus 3, which is also n plus 1, n minus 1 plus 2, which is also n plus 1, and n plus 1, which is also n plus 1. How many n plus 1s do I have added together? N of them, right? There's 1, 2, 3, all the way to n terms, so I have n of these things. That's going to be equal to n times n plus 1. And so then, if you divide both sides by 2, oh, wow, can I write a summation notation? Maybe. The sum from I equals 1 to n of I, which again is just 1 plus 2 plus 3 plus all the way to n, is equal to n times n plus 1 divided by 2. Kind of cool. People call this a triangular number. It's also called the handshake number, because if you have a group of n people, it's the number of handshakes that take place if everybody shakes everybody else's hands. Kind of cool. So if there's like 5 of us, well then 5 times 6 over 2 is 30 over 2 is 15. There'd be 15 handshakes. I would shake, that seems wrong. I feel like there's a, no, yeah, that feels like 5 of us, that's 4, yeah. I'm missing something there. I'm off by 1, but don't worry about it too much. Yeah. So, question.
Yeah, I'm just so confused when you would use this equation, like what you.
We're going to get there. It's going to take a minute, but we're going to get there. But so the bigger answer is we're going to use this equation when we use the limit definition of the integral to actually calculate the area under a curve. But there's a few things we have to build up before we can say that. So yes. So I will point out there is another formula which is provable, but it's kind of a pain. I don't think we want to spend time doing it right now in class, but I'll tell you there's two more formulas that you might be expected to use. The sum from I equals 1 to n of I squared is 1 squared plus 2 squared plus 3 squared plus all the way to n squared. And that's equal to n times n plus 1 times 2n plus 1 divided by 6. And there's one more that might come up. Well, there's one more that might come up that's like, that's hard to just know. I think this is one of the neatest things in math personally. If you add up all the cubic numbers, so 1 cubed plus 2 cubed plus 3 cubed, all the way to some n cubed, what you get is that number squared. You get n times n plus 1 over 2 squared. So just as a quick aside here, go back to the anchor days page for 1 second here. This is kind of neat. So for example, 1 cubed plus 2 cubed plus 3 cubed. That's 1 plus 8 plus 27. That's 36, which is the same as 1 plus 2 plus 3 squared. 1 plus 2 plus 3 is 6. 6 squared is 36. And it works no matter where you stop. If you go up to the next one, can you see that? No, you can't. 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is 36 plus 4 cubed, which is 100. And that's the same as 1 plus 2 plus 3 plus 4 squared. I just think that's really neat. But if you add up all the cubic numbers, it's the same as first adding up all the numbers and then squaring it. Kind of neat, kind of weird.
I have a question.
Fun patterns in math. Okay, a couple more things we need to know with the summation notation, and then we will leave it behind and come back to it later. So a few more easy examples. If I do the sum from I equals 1 to 5 of 7, when I equals 1, oh, question, sorry. And if I don't see you raise your hand, just say, hey, James, I have a question. I will, sometimes I don't. Oh, also, sorry, what, go ahead. Yes. So I will tell you that's a formula that we're gonna accept for now. I will maybe I can either find or write up a proof of it, for lack of a better term, to kind of show you where it comes from. But it is a not easy formula to derive on its own. And I believe, at least in the Dallas class, if you look at the solutions to the discussion handout that he posted, he does show the work of doing it by induction, which I think is not my favorite way of doing it, but it works just fine. But yeah, it's a little bit complicated. But it does, but that is the correct formula. And sorry, there's some things on. So if you're on the chat and I don't see what you've written because sometimes it's just not where I'm looking, I will. Let's see. Let's see. Could you repeat the last example? So I'm not sure which example you're referring to. How do we know what to guess for derivatives? That's for guessing for antiderivatives, I know it was a minute ago, I'm thinking about really what the derivative was. So I'm usually kind of thinking about the derivative of the function and where that might have come from. And then someone just asked where the 2 came from. Sorry, I'm sorry, I'm not sure what these are a reference to because I missed them. So if you're on the chat and I'm not seeing your question, you really, really, really are welcome to unmute yourself and say words. And oh, my volume's turned down, so you might have done that. I might not have heard you. Sorry if you did that. On the first summation derivation, let's take a look. You mean the one right here? Yes, no, maybe so, yes. So the 2 came from the fact that I was adding these two things together. So I was doing this summation plus the same summation gave me 2 of those summations. And then on the right-hand side, I was adding. That's how I was coming up with that. Cool. All right. So for some easier things, for the sum from I equals 1 to 5 of 7, I'm going to plug in I equals 1 and get what? There's nowhere to plug it in. It's like plugging into a constant function. You're just going to get the constant value. So I'm going to get 7 when I equals 1. And when I equals 2, I'm going to get 7 again. When I equals 3, I'm going to get 7. And when I equals 4, I'm going to get 7. When I equals 5, I'm going to get 7. If you're doing a summation of just a constant, you're just going to get that constant however many times you're doing the summation, which in this case is there's 5 things to add together. So you're going to get 5 times 7, which is 35. More generally, we can say that if we're doing the sum from I equals 1 to n of some constant c, we're just going to get c added to itself n times, which is just going to be n times c. And I think that's really all I want to say. Yeah, we could do that, but okay, one more other interesting thing, and then we will move on. Yeah, one more. So there's also something called a telescoping sum. Something, and this is useful if you want to actually do the proof of the thing we're talking about, which is why I want to mention it right now. So I was doing the sum from say I equals 1 to, yeah, let's make it big. Let's do I equals 1 to 40 of the square root of I plus 1 minus the square root of I. It's a lot of things to write. I'm going to start writing it. I'm going to get, let's see, if I plug in 1, I'm going to get the square root of 2 minus the square root of 1 plus, then I equals 2, square root of 3 minus square root of 2, plus bump up to the next one, square root of 4 minus square root of 3, all the way to the last 3 terms maybe. So let's see, when I equals 38, I'm going to get the square root of 39 minus the square root of 38. When I equals 39, I'm going to get the square root of 40 minus the square root of 39. And I've not quite left myself enough room here, unfortunately. When I equals 40, I'm going to get the square root of 41 minus the square root of 40. But what happens in a telescoping sum like this is a lot of things cancel out. The square root of 2 and the negative square root of 2 add to 0. The square root of 3 and the negative square root of 3 add to 0. The square root of 4 and the negative square root of 4 that would have been in the next term add to 0. And similarly, all the way through up until the end, the negative root 39 and the positive root 39 cancel out. The negative root 38 and the root 38 that would have been in the previous term cancel out. The negative root 40 and the positive root 40 cancel out. So we end up with just the square root of 41 minus the square root of 1, which is some number that's a little bit bigger than 5. I would simplify this slightly because the square root of 1 is just 1. But the point here is that when you have a telescoping sum like this, where you have 2 things subtracted and one of them is just like one more term later than the previous one, you typically get this pattern of all these middle terms canceling out, and you're just left with the kind of the end term minus the beginning term, which is nice and useful for proving things later on if we need to prove them. But what I really want you to know about summation notation is kind of the thing I said first, which is that if you have a sum of things added or subtracted together, you can break those apart into 2 things, and any constant multiples can get factored out in front. That comes up quite a lot. All right. Yeah, enough of that. Okay, cool. I'm just making sure. Yeah, that seems good. All right. So now we'll get to the area under the curve stuff. So area under a curve. I did, for those of you that looked for it, I didn't do it right away, but I did link that summation notation, or sorry, not summation, that Riemann sum link that I was mentioning in class the other day. I don't know if everybody saw that. This is a reminder. This is what I'm referring to. This thing here, right? I mentioned this in class the other day. See, so I might not. So, okay. So the truth is, I'm teaching this class. I'm also teaching a Co-21B class, and a lot of the material in the beginning is like exactly the same. So I might have said something in the other class that I thought I said here. So it's okay to be like, no, James, we never saw that. You must be talking about the other class. Did I mention this in this class? No. Okay, that's totally fine. So there's a link to this on Canvas. I think it's super neat. You can use this to estimate the area under a curve and kind of see what the Riemann sums actually look like. So let's look at a nice example here. Let's not choose this crazy function. Let's pick something that's easier to look at, like say, I don't know. Sure, 4 minus x squared. Cool. And we don't want to go from 0 to wherever. We want to go from 0 to 2 because that seems more interesting. And then maybe I only want to use like, I don't know, 4 rectangles. And I'm using, so my first rectangle has a height of something, I don't know. But what I want you to see here is that, if I can get there, right now I'm using right endpoints, right? For each subinterval, I'm taking the right endpoint of that subinterval and then using that endpoint to find the height of the function. Same deal for the second subinterval, same deal for the third, same deal for the third subinterval, and same deal for the fourth subinterval, but the height there is just 0, so you don't really see a rectangle. Or I could slide this over to the left and use left endpoints. And then I'm seeing a different estimation, but still the same idea. For each subinterval, I'm taking the left endpoint, using that endpoint to find the height, and then finding the area of the rectangle and adding all those areas together. And you could even use midpoints. It does show up if you get there. Or really any point in between. And that's what your professor means when they use that xi star notation, is that xi star is just any point in the subinterval. I could go a little bit to the left of the middle, a little bit to the right of the middle, kind of anywhere you want, and they don't have to be the same. So this is a nice tool to look at if you're trying to, and also you could also use it to check your work if you wanted to, right? You could tell that I had to estimate the area under this curve using 4 subintervals with right endpoints, and I did the work. Now I'm going to go look at this and see, like, did I actually get it right? This won't give you exact values, meaning if your answer is like the square root of 1 plus the square root of 2 plus the square root of 3 plus the square root of 4, that's the answer you should write. This will do a decimal approximation of that, but you would have to then use a calculator to see if they were the same value or not. But still, I think it's nice and useful. That said, let's talk about doing some stuff. I feel like this could be slightly brighter. And I hate when I do that. There we go. All right. It's 9:35, cool. So area under a curve. So let's do the following. Let's get that. Terrible. Sorry. Always with the things. Yes. And also, yeah, I'll try to look at the chat here just to make sure I don't miss anything, but it's never really in my line of sight. So I wish there was a way to like make a noise. Maybe there is, I'm not aware of, but we're not there right now. So I'll figure that out later. Let's say we want to do the following. Let's say we want to estimate the area under f of x equal to the square root of x using, use a different pen, x equals 0 to x equals 16 using n equal to 4 rectangles. We'll start on the first example, right endpoints. Okay, so I'm going to draw the curve. Square root of x is pretty nice. That's this usual kind of shape. And I'm going to say 16 is about right there. So we're going from 0 to 16. I want to break this up into 4 equal subintervals. So the way we do that typically is we find our width of our subinterval, which we call delta x. That's going to be generally b minus a divided by n. In this particular case, that's going to be 16 minus 0 divided by n equal to 4, which does end up being 4. So each of my subintervals has a width of 4. So when I have to break something up into 4 equal subintervals, I'm actually trying to draw it. The easiest way I have found is to cut it in half visually and cut each of those in half visually. That's the easiest way to break something up into 4 or 8 or anything that's a power of 2. So then each of these are 4 apart. So my left endpoint is 0. And then the next endpoint is 4. 4 plus 4 is 8. 8 plus 4 is 12. 12 plus 4 is 16. Some notation. The leftmost endpoint we always refer to as x sub 0. And then we just increase the index on each of them. So the next one is x sub 1. The next one is x sub 2. The next one is x sub 3. And the last one is x sub n, which is x sub 4 in this case. Each of these endpoints of our subintervals are delta x away from each other. So now I'm trying to estimate this area. I'm going to use rectangles, and in each subinterval in this problem, I'm using the right endpoint. So for this first interval from 0 to 4, I'm going to use the 4. I'm plugging in 4 to my square root function and using that height as the height of my rectangle. Same deal for the next subinterval. 4 to 8, I'm using the right endpoint to get the height of the function and then get my rectangle. I don't really need to shade that in, but started doing it, so. Next subinterval from 8 to 12, same idea. Use the 12 to find the height. Finally, last subinterval from 12 to 16, use the 16, find the height of a rectangle. So then if I actually want to write out what this is, I'm going to write it as the area is approximately equal to, I typically use the notation for this, R sub 4. That's not always what people do, but that's what I like to do, where R is for right endpoints and the 4 is for 4 subintervals. If I was using left endpoints, I would say L sub 4. If I was using midpoints, I would say M sub 4. It's fairly typical, but not everyone uses that notation. So I'm just finding areas of rectangles. Great. The first rectangle, the height is f of x sub 1. The base is delta x. Second rectangle, the height is f of x sub 2. The base is still delta x. The third rectangle, f of x sub 3 times delta x. The fourth rectangle, f of x sub 4 times delta x. I'm writing it in this generic way so that we can kind of see that this sort of pattern is always going to hold. In fact, I could also factor out the delta x and write this as delta x times f of x1, the first right endpoint, plus f of x2, the second right endpoint, plus f of x3, plus f of x4. And then we could actually use the values that we have and say, okay, well, our delta x is 4. F of x1 is f of 4, which is going to be the square root of 4. F of x2 is f of 8, which is the square root of 8. F of x3 is the square root of 12. F of x4 is the square root of 16. Yes, we could simplify the square root of 4 as 2 and the square root of 16 as 4. It's not really pertinent. I would point out more interestingly that this is approximately equal to 49.17. Clearly from our picture, an overestimate or an underestimate? Definitely over, right? There's more area in the red rectangle than in the black area under the curve. That's not to say that right endpoints will always give you an overestimate, but they will always give you an overestimate if your function is increasing like this. Because if it's increasing, the right endpoint will always be the point where the function is the highest in that subinterval. If it was decreasing, right endpoints would give you an underestimate. And then if it's not increasing or decreasing, like if it goes back and forth, then you can't really tell from the thing. What about if we used left endpoints? Try to make this semi-quick. Keep grabbing the wrong pen. The same idea using, sorry, let me label this, left endpoints. So I'm going to draw the same thing from 0 to 16. We're going to break it up again into 4 equal subsections. Where x sub 0 is still 0, x sub 1 is still 4, x sub 2 is still 8. Sorry, my writing's getting a little bit sloppy here. X sub 3 is 12, x sub 4 is 16. But now, for each of these subintervals, we're going to use the left endpoint to find the height. So here, our rectangle is kind of terrible looking. It doesn't even really look like a rectangle because the height is 0. So there's your rectangle at the height of 0. You can kind of see it. And then for the next subinterval, we're using the left endpoint to find the height at f of 4, which is f of 4. For the next subinterval, we're using the left endpoint, go up to the function and then over. And then finally, for the last subinterval, we use the left endpoint. So there's our picture depicting what our estimate using left endpoints with 4 subintervals is going to be. And we can see here that our area is going to be approximately L4, which is going to be, I'm going to write it as delta x times f of x sub 0 plus f of x sub 1 plus f of x sub 2 plus f of x sub 3, which is going to be 4 times the square root of 0 plus the square root of 4 plus the square root of 8 plus the square root of 12. And that's going to be approximately 33.17. A pretty wide margin between our two estimates, right? I mean, from 33 to 49, right? That's a lot of potential values in there that could actually be the number. So then the question becomes, actually, I should say, are there questions before we continue on? I should just keep going. It's a bad habit of mine to stop and ask a question. You will ask questions if you have them. You should ask questions if you have them. Yes, question. Definitely. Of course. And just as a point of clarification, you're welcome to take pictures over there, right? I will also point out to everybody, I do post the lecture notes from class. So if you want to see them later, they will be available. But yes, you can take pictures if you need to. But I'm not going to stop for pictures. So if you want to take them, you'll have to catch them as you can.
I had a question about on like quizzes and stuff. Are we
On
gonna
what
be
stuff?
like expected, because I know we don't get a calculator for them, are we gonna be expected to like fully calculate like 4 times?
So if
Square root
someone
of
had
X
asked
and
you to
stuff.
do this problem exactly on an exam, I would have stopped right here. I might have gone one step further and written this as 4 times the square root of 4 is 2, the square root of 16 is 4, 2 plus 4 is 6, plus root 8 plus root 12. But without a calculator, there's nothing else we can do, and that's where I would stop.
Okay, thank you.
Welcome. Same deal here, right? If I really wanted to write this in a nicer looking way, although really you shouldn't. If you're told to do a problem like this on a test, you should stop here. There's no value added, in my opinion, to writing this as 2 plus root 8 plus root 12. You're not displaying that you have any more knowledge about the process by doing this than if you left it right there. Unless they specifically say you have to simplify everything as much as possible, then you should do it. But usually that's not what people are looking for when they're asking you these sorts of questions. So the area under f of x equal to the square root of x from x equals 0 to x equals 16 is between 33.17 and 49.17. How do we get a better estimate? Yeah.
You take the integral of the original equation.
Well, I don't want a perfect answer yet, but we're going to get there eventually. How do I just get a better estimate? That would be a good way to do it. What's another way we could find a better estimate?
Find the average?
More sections. Yeah, finding the average is also good. So actually, it's interesting because the midpoint and the average seem like the same kind of thing, but they're actually not quite the same thing. So you could take the average of these two estimates. That would certainly be a better estimate. You could use the midpoint of each of the subintervals. That would also usually give you a better estimate. But the thing that we're actually going to do to get a better estimate is use more subintervals. So instead of using n equal to 4 subintervals, we could use n equal to 8 subintervals. So we're going to use more subintervals to get a better estimate. So this is where I'm going to try to draw. Yeah, sure. I can draw the thing. So let's say we want to find R sub 8, the estimate of the area under the curve using 8 subintervals with right endpoints. And we're going to try and do this somewhat rapidly here. Not that we're running out of time, just there's lots of things to say. So here's our usual thing. I'm just going to stop right at 16. We're going to break this up into 8 subintervals. So our delta x, the width of each subinterval, is going to be 16 minus 0 divided by 8, which is going to be 2. So each subinterval is 2 away from each other. Again, I'm breaking this up into a power of two things. So here's the easy way to draw it, I think. Cut it in half, cut each of those in half, cut each of those in half. So then starting 0 and then 2, 4, 6, 8, 10, 12, 14, 16. Again, just for the sake of notation, because this does come up, our 0 is x sub 0. Our 2 is x sub 1, our 4 is x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, x sub 8. You should always be starting with x sub 0 and ending with x sub n, where n is the number of subintervals. I should write that right. N equals 8. And I'm using right endpoints, so here's what my thing is going to look like. I was using red before. Let's use red again. All right, red doesn't really cover up blue very well. Let's draw this the fastest way possible by first drawing the vertical parts. And then going over like that. And my drawing skills are not always great, but they're okay. Had many years of practice. So I want you to notice, compared to the previous estimate using right endpoints with 4 subintervals, we've got a lot less error, right? Over here, there's all the error, and that's quite a bit, right? That's our overage right there. Whereas here, we've got less overage. We're cutting out kind of all of this stuff right here. So we just have this bit here, right? It definitely looks like it is less because it is less. And that's how we're going to get a better and better estimate, letting n get larger and larger and larger. If we actually calculate this, the area, which is approximately R8, is going to be, okay, we're just going to cut to the chase. It's going to be our delta x times f of x1 plus f of x2 plus all the way to the very last right endpoint, which is f of x sub 8. And that's going to be 2 times the square root of 2 plus the square root of 4 plus the square root of 6 plus all the way to the square root of 16. And using a calculator, we're getting approximately 46.12. And I think I've drawn enough pictures. Let's just find L8 instead of writing it down. So to find L8, well, we're going to use left endpoints. So really, it's almost the same exact calculation, except instead of starting at x1, we're going to start at x0. Instead of ending at x sub 8, we're going to end at x sub 7. So that's going to be delta x times the left and the first left endpoint, the second left endpoint, all the way up to the last left endpoint, which is x sub 7. That's going to be 2 times the square root of 0 plus the square root of 2 plus all the way to the square root of 14. And again, using a calculator, we're going to get approximately 38.12. So still, right, not super close to each other, but closer than our previous two estimates, right? We've narrowed the gap or the range of what our possible area actually could be. So then really the question becomes, well, how do we make this better? Like, how do we get there really? Well, we're not going to do it for this one because this one we can't actually, we could do, but it's more complicated. Yeah, time. Sorry, I'm trying to like use my time efficiently here. But I guess I should point out, we could also find this using midpoints. So let's show the midpoints just so that everyone can see the midpoints, and then we will move on to the actual calculating because I want to get there. So what if I wanted to find or estimate the area? I want to estimate the area using n equal to 8 subintervals and midpoints. So I am going to draw it again. The reason people don't like midpoints, at least the reason I don't like midpoints, is it means you have to find additional points, right? We don't just get to use our x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. x sub 5, x sub 6, x sub 7, and x sub 8. You then have to go find the midpoints of each of the subintervals, which in this problem aren't that bad because they're really just the odd numbers. But the midpoint here is 1, and then 3, and then 5, 7, and 9, and 11, and 13, and 15. And the idea is for this first subinterval from 0 to 2, we're going to use the midpoint and get the area of that rectangle. And then from 2 to 4, we're using the midpoint and getting the area of the rectangle with the base from 2 to 4 and the height being f of 3, and so on and so on. Right. It's always a little, the repeated drawing gets to be a little tedious. You're like, okay, we can draw this again. So here's all of our rectangles. And in this problem, you can see that all these rectangles are going to be a little bit over and a little bit under. The left half is over, the right half is under. At least that's how it should look. It's a little sketchy at the end here. Sorry, the last one's not that great. Oh well. So there are 8 rectangles, and the area using 8 midpoints is still going to be delta x times, but now it's going to be f of the midpoint. So I think he did this in class, or at least Del did this in class by saying it was like x sub I minus 1 plus x sub I divided by 2. Seems like an annoying thing to write. Here's another notation people use, which you might be familiar with if you've ever taken any class where you talked about an average ever. I'm going to do f of x1 bar, for the average of the endpoints of the first subinterval, plus f of x2 bar, plus all the way to f of x sub 8 bar. I feel like that's not wonderful. I feel bad about this notation now that I've written it because, but that is the way it gets written, unfortunately. So here we're going to have, I'm sorry, I'm saying things that I don't actually mean. That's totally fine. Yeah, that's fine. Yeah, I don't feel bad about the notation. So we're going to get 2 times square root of 1 plus the square root of 3 plus the square root of 5 plus all the way to the square root of 15, which we may have calculated. No, we may not have calculated. No, we didn't. So that's something. Another approximation. But the point here really is just that, yes, you can use midpoints. So then we ask, how do we find the actual area? Well, that's when you start taking the limit. So you find the actual area under the curve. We let the number of subintervals n approach infinity. As the number of subintervals gets larger and larger and larger, each subinterval gets narrower and our error gets smaller and smaller and smaller until it becomes inconsequential. The math of actually doing this is a little bit terrible. So there's no other way to say it. It's a little bit terrible. Like it's a kind of big process and there's a lot of writing and we're going to do it. But it is a little bit terrible. But we're not going to do it for this example because it just doesn't really come out very nicely. So here's how we're going to write the things. Finding the actual area under the curve. Not estimating, but finding actual. So here's how we're going to write it. We've got some function, f of x, and we want to find the area under f of x between a left endpoint of A and a right endpoint of B. So our job is to find this generic area here. And here's how we're going to write this. So the area under f of x between x equals A and x equals B is expressed as the integral from A to B of f of x dx. Yes, that is the same symbol I've been using to write the antiderivative. And there's a good reason for it that we'll get to when we talk about the fundamental theorem of calculus. All right, so the way we're going to calculate this right now is in the hardest way possible. We're going to take our estimate, which is the sum of all of the areas of the rectangles. So that's going to be each height times each base. And then we're going to add those all up from I equals 1 to n. So this is just a way of compactifying the right endpoint formula, right? This is really, if I write this out, this is f of x1 times delta x plus f of x2 times delta x plus all the way to f of xn times delta x. N rectangles, each with a base of delta x and with different heights, f of x1, f of x2, f of x3, and so on. Am I using left endpoints or right endpoints here? I'm using right endpoints, right? Because the first, if you go back here, right? When I was using left endpoints, I started at x sub 0. And when I was using right endpoints, sorry, I started at x sub 1. But you could do it using left endpoints. Or you could do it using literally any point in each subinterval, which is, I think, the way they typically express it in class or in the book. They like to write it as this. Can you see that? Yeah, you can see that. The sum from I equals 1 to n of f of x sub I star times delta x. And the only difference between x sub I and x sub I star is that x sub I is actually the right endpoint. X sub I star is any point, and then spell point right, in the ith interval, meaning any point between x sub I minus 1 and x sub I. So if you're drawing out your little picture here, and you've got, let me actually draw it. Yeah, sure. I can maybe, yeah, let's just say we have the ith interval here. X sub I star is any point in between those 2 points of your ith subinterval. That's the idea. And the reason it doesn't matter is because if you let the number of subintervals get infinitely large, each subinterval gets extremely narrow. And so it doesn't matter if you pick the left endpoint or the right endpoint or some point between them, because they're all exactly smashed up against each other and they're the same point. Yeah. Correct. Yes. And unfortunately, people do an annoying thing sometimes, which is they say, if I want to use left endpoints, they either, if they're doing it the nicer way, they write it as the sum from I equals 1 to n of f of x sub I minus 1 times delta x. But if they're doing it the maybe slightly less nicer for you way, they might write it as the sum from I equals 0 to n minus 1 of f of x sub I times delta x. It still gets you the same thing, right? This one starts at f of x sub 0. This one starts at f of x sub 0. This one ends at f of x sub n minus 1. This one ends at f of x sub n minus 1. But it's a different way of writing the same thing. Now, of course, I've forgotten one really important thing here. These aren't equal to each other unless we let the number of subintervals get infinitely large. So you have to take the limit as n goes to infinity of this summation. Now, unless there's a good reason to do it a different way, and by a good reason, I mean someone has told you explicitly you have to do it a different way, you should do it using right endpoints because it's usually the easiest. Okay. So let's look at some examples here. Yeah. Cool. We're going to do it. So we're going to use, the limit definition of the integral, which is what we just wrote down. To find the area under f of x equal to 2x plus 3 from x equals 1 to x equals Sure, 5. And before we do it the long way, we're going to be smart and we're going to do it the graphical way. Sometimes there are functions that you don't have to actually do any sort of integration to find the area under because they look like shapes you already know the area of. This is a shape we might all be familiar with. So if I graph y equals 2x plus 3, that's just a straight line with a slope of 2. I'm going to draw it so the slope is actually doesn't look quite like what it should be because I want more room. But here's my function. F of x equal to 2x plus 3. And I'm trying to find the area under this function between x equals 1 and x equals 5. I'm trying to find this area, which I will point out you could think of as the area of a rectangle and a triangle. Or you could think of it as a trapezoid. I never remember the area formula for a trapezoid, but I definitely know the area formula for a rectangle and a triangle. So I have a rectangle whose base is 5 minus 1, and whose height is, let's see, if I plug in 1 here, f of 1 is 2 plus 3, which is 5. So that's the point 1 comma 5 right there. So the base of the rectangle is 4, the height of the rectangle is 5. I know it doesn't look like that because I've scaled things weirdly. It's fine. And then for my triangle here, the base is 4, and the height is, well, I have to find how high it is here. So if I plug in 5, 2 times 5 is 10, plus 3 is 13. So the height of this triangle is 13 minus 5, which is 8. So the area of this triangle is 1/2 the base, which is 4, times the height, which is 8. So I'm getting 20 plus 1/2 of 32 is 16. I'm going to get 36. Cool. So I know that the answer should be 36. But now we're going to do it the long way. And yeah, we have enough time. Okay. So we're going to draw this using not 4, not 8, not 16, but n subintervals. And yeah, I think I want more room. I want more room. I'm going to draw this again. I'm going to give myself even more horizontal space to draw my function here. Here's the same function, f of x equal to 2x plus 3 from x equal to 1 to x equal to 5. And I'm going to break this up into n subintervals. So here's what my drawing is going to look like. So this first value here, this is my a, which we also call x sub 0, right? Our left endpoint is our starting point. It's always x sub 0. Our last endpoint is b, which we're also going to call x sub n. And then I'm going to break this up into n equal width subintervals. So I'm just going to kind of draw them at a convenient width apart from each other. I usually draw like 3 or 4 of them, and I kind of do this dot, dot, dot kind of thing. We got this, dot, dot, dot. There's one in the middle, and then a few more, and then the very last one. Okay, so let's label things. Let's draw the rectangles. And I used blue accidentally. Oh, well. There's my first rectangle using a right endpoint. Second rectangle using a right endpoint. My third rectangle using the right endpoint for the height. My fourth rectangle using the right endpoint for the height. And I want to point out that when you use right endpoints, the number of the interval, like the first subinterval, the second subinterval, the third subinterval, the fourth interval, corresponds to the number associated with the right endpoint. So the right endpoint of the first subinterval is x sub 1. The right endpoint of the second subinterval is x sub 2. In fact, we could label things here. The right endpoint of the nth subinterval is x sub n. And for the ith subinterval somewhere in the middle, the right endpoint is x sub I. The left endpoint is x sub I minus 1. Our delta x here, which is the width of each subinterval, is b minus a divided by n, which in this case is 5 minus 1 divided by n, which is 4 over n. And n is just n. It's not an actual number. It's just the placeholder for whatever number you want it to be, which eventually is going to get really, really large.
Quick question, just to
Yeah.
double, x of 1 is a? Or,
X sub 0 is a.
so,
That's right, it's written, so right here. So a is equal to 1 and x sub 0 is equal to a. And I didn't quite make it super clear there, but you can kind of see that.
so how come we didn't draw like the, how do I say this? Like the rectangle to the left of that x1, like,
Well, because we're not starting at 0. So I know in the previous examples, we did do the interval from 0 to 16. But now we're going not from 0 to 16 or from 0 to 5, but we're going from 1 to 5. So we're starting at 1. And all this over here is not what we want at all. We don't want any of this over here either. We're just looking, I didn't finish drawing my rectangles here, sorry. We're just looking at these rectangles here. That's all we're interested in.
okay, thank you.
You're welcome. So now we're going to write, oh, question, yeah.
Do you know how much like rectangles?
I just drew a few. So what I really usually drew and again, usually you're not actually going to draw the rectangles for this n subintervals thing. But if I had to draw them, I would draw 3 or 4 in the beginning, some dots, an ith one in the middle, some more dots, and the last one at the end.
You just do that for like every.
If it's specifically n subintervals, meaning we don't actually know the number. Okay. But now let's just write the area. Right? The area here is going to be our approximation using these right endpoints is going to be, well, the first one is going to be delta x times f of x sub 1. In fact, let's just factor out the delta x and say it's delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus all the way to f of x sub I plus all the way to f of x sub n. Great. We don't want to write all that. Let's make it better. Let's write this as delta x times the sum from I equals 1 to n of f of x sub I. Same thing, right? That's f of x sub 1 plus f of x sub 2 plus f of x sub 3 all the way to f of x sub n. There's no reason this delta x needs to be out in front, and it's usually written not there. It's usually written as the sum from I equals 1 to n of f of x sub I times delta x, like that. I want to re-emphasize, all we're doing is adding up a bunch of areas of rectangles. That's a base times a height plus a base times a height plus a base times a height, n times. And now we're actually going to fill in the pieces, right? Our function here, you go back for a second, our function is the integrand, the thing we're integrating. So f of x is 2x plus 3. We found delta x, I'm going to write it again. Delta x is 4 over n. And then the x sub I part is always probably the hardest part for people to figure out what it is. There is a formula for it, but I just want to show you what it is. So I'm going to point out, you see that? You can't see that. So x sub 0 is a, which is 1. X sub 1 is 1 plus, well, we moved over delta x, which is 1 plus 4 over n. X sub 2 is 1 plus, well, then from a equals 1, we've got 2 delta x's, which is 1 plus 2 times 4 over n. And we start to see the pattern. X sub 3 is 1 plus 3 delta x's, which is 1 plus 3 times 4 over n. And then we go down to the x sub ith one, which is 1 plus I times delta x, which is 1 plus I times 4 over n. Sorry, my 4's and my n's sometimes start to look like each other. I will try to make them look distinct. And finally, I like this as a check. If I go all the way down to x sub n, it should be 1 plus n times delta x, which is 1 plus n times 4 over n. But n times 4 over n is 4. And 1 plus 4 is 5, which is where we should be ending at. So that's good. It seems right. Okay, so now we're going to rewrite this as the sum from I equals 1 to n of f of our x sub I which is 1 plus 4i over n, times our delta x, which is 4 over n. And then we are going to replace this with actually plugging in the 1 plus 4i over n into our function. So f of x is 2x plus 3. F of this is going to be, well, 2 times 1 plus 4i over n plus 3. Still times 4 over n. So now, I'm going to point out again, this is just the height of the ith rectangle. This is just the base of the ith rectangle. And we're adding up all of the areas of each of the rectangles, from the first rectangle to the nth rectangle. And then we're going to take the limit of that. And yeah, we have enough time, which is good, because it'd be terrible to leave this cliffhanger. So, to calculate the area here, the area from 1 to 5 under the function 2x plus 3 is equal to the limit as n goes to infinity of the thing we just wrote right there. The sum from I equals 1 to n of 2 times 1 plus 4i over n plus 3 all times 4 over n. Which looks kind of gnarly, but it's what we've got. So now the rest of this is a bunch of algebra that where you break apart this thing into pieces and then eventually get something that looks like something we can use a formula for. So bear with me while we break this apart. So we've got the limit every time. We do have to write the limit every time, or alternatively, you could just work with this for a while and then at the end say, oh yeah, limit of that. Let's multiply this out. I've got the sum from I equals 1 to n of 2 plus 2 times 4i over n is 8i over n plus 3 all times 4 over n. I'm going to rewrite that as the limit as n goes to infinity of the sum from I equals 1 to n. 2 plus 3 is 5 plus 8i over n times 4 over n. I'm going to distribute the 4 over n and get the limit as n goes to infinity of the sum from I equals 1 to n of 20 over n plus 32i over n squared. This is where I always stop to check. And the thing I am checking for, if I'm actually having to do this process, is that in each fraction I have after I multiply out the insides, the power of I should be 1 less than the power of n. So I've got I to the first over n to the second, good to go. I've got I to the 0th over n to the first, I'm good to go. As long as that's true, you're on the way to getting to the right place. Okay, so now we're going to do the thing that I said we were going to do. We're going to break this apart into two summations. It's going to be the sum from I equals 1 to n of 20 over n plus the sum from I equals 1 to n of 32i over n squared. And as far as these summations are concerned, n is a constant. N is just some number. It could be 5, it could be 50, it could be a billion. But it's a constant, meaning it can come out in front. So I can rewrite this as the limit as n goes to infinity of 20 over n times the sum from I equals 1 to n of 1 plus 32 over n squared times the sum from I equals 1 to n of I. And the reason we have done this is that we know the formula for the sum from I equals 1 to n of I. It's n times n plus 1 over 2. And we know the formula for the sum from I equals 1 to n of 1. It's 1 plus 1 plus 1 n times, which is just n. So we're going to get that this is the limit as n goes to infinity of 20 over n times n, which is just 20, plus 32 over n squared times n plus 1 over 2. I would point out that I don't think you need to multiply this out to see what the answer is going to be. But in case you might have forgotten, well, actually, let me do one more thing here. I'm going to write this out as the limit as n goes to infinity of 20 plus 32 times n plus 1 over 2n squared. Limit of 20 is 20. I don't really want to multiply this out, especially when it's like the bigger formula with the n times n plus 1 times 2n plus 1. If we multiply it out the top, what would the highest power of n be? 2. We'd have n squared. What would its coefficient be? 32. On the bottom, the highest power of n is n squared. Its coefficient is 2. And when you have a limit as something goes to infinity of a rational function and the powers are the same, the limit is the quotient of the leading coefficients, meaning this is going to be 32 over 2, which is 20 plus 16, which is 36, just like we said it was. Now, you might say, why would you do all this work when you could do it in an easier way? Because not every function's area can be found so easily. Not everything breaks up into a triangle and a rectangle. So there are more complicated functions, which we'll try to talk about on Tuesday, like a square function, where you can use this as well. The last thing I'll say here is, just in case you've forgotten how I've gotten here, I'll remind you that if I was going to find, say, the limit as n goes to infinity of 2n cubed plus 5n squared plus 6n plus 1 over 7n cubed plus 4n plus 8, we would know right off the bat that that limit was going to be 2/7, because the degree on top and the degree on the bottom are both the same, and the limit is the fraction or quotient of those leading coefficients. Question? You can do kind of either way. So my preference would always be to write it as a summation, like sigma notation, because that's less writing to do. But you can certainly write it out to kind of remind yourself what is happening. All right, it's 10:20. That means I should stop talking. So I will see you all on Thursday. Definitely make sure so the first reflection, I believe, closes tomorrow at 4. Make sure you do it by then. And then the second reflection will open, or might have already opened. Please do that over the weekend. Let me know what you would like to see me talk about, or on Monday, maybe, if you like, so that I know what you want to see happen on Tuesday. I have office hours over in C class right now from 10 in C class, 10:45 to 11:45. That's all for today. See you all later. Make sure you fill out the attendance form. If you didn't already, you can scan it there or there. I do recommend bookmarking it. Here it is for those of you on Zoom, in case you didn't already get it. Whoops, no one had that just yet. What's that? You would think I would, because I've been around for so long, but I don't actually like I'm sure his quizzes look the same as they have like for a lot of quarters, but I don't actually know what they look like.
Discussion sheet that he gave us, or just the homework?
I mean, I guess I would start with the homework, and then if you have time, work on the discussion sheet. When is the quiz? Okay. What did he say about the quiz? I feel like there was something written in Canvas about like
It was just, to focus on section like 4.9 or something.
4.6 maybe?
4.6.
Yeah, so that to me that says anti-derivative. Excuse me, anti-derivative. So that's probably what you should focus on. Yeah, okay. So,
Question, that last example, I was a bit confused how you got back n plus 1 over 2. You had a
sure.
example here?
So what I did was I simplified the summation down to the part where I had factored out all of the
Yeah,
constants.
I was confused how you got this back.
Well, because that's the formula for this. So if you add, right, if I look at just that, that just means 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way to n. And we talked about in the big earlier on how if you add up 1 through n, you get n times n plus 1 over 2. It's coming from.
So basically, you brought this, you made this into this.
Right, because that's what it's equal to. Right, so sorry, it's back here somewhere. Right, we talked about how, right, the sum from I equals 1 to n of I is equal to n times n plus 1 over 2.
Yeah, because like 1 plus 1.
2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus all the way to whatever your n is equal to n times n plus 1 over 2.
Okay. Okay, got it. Thank you.
You're welcome.
I'm just wondering, in the beginning, when doing the examples, it was like n times n